In this video, we're going to discuss truth tables. Now, what are truth tables? Well, truth tables will tell us all possible outcomes of statements and connectives. So, for instance, let's recall that each statement is either true or false, and true is a 1, false is a 0. We have some statements here, like 32 is even, and this just has a truth value, so this is true, which we can do with a t, or we can do with a 1. I'll show you both now. And then we have another statement, like A is a subset of B if and only if X in B implies X in A. This is false. It is in fact the other way around, so we can do an F or a 0. And these are really specific statements. But what happens if we want to think about truth values for more general statements? For instance, what if we had X is even and we want to think of all possible outcomes? Well, this is what truth tables are for. And all connectives take a truth value and output a new truth value. So depending on the connective, the truth values can change. Let's take a look at each connective individually and see how this affects our truth values. So first of all, we have a truth table. And a truth table shows all possible combinations of truth conditions. So for instance, P can either be true or it can be false. So what does negation do? Well, if P is true, then the negation of P is going to be false. If P is false, then the negation of P is going to be true. So we can see that what the negation does is neg P just takes the value of P, or should I say, it takes 1 and then subtracts P. So for instance, if P is equal to 1, as in the first row here, then not P is equal to 1 minus P, which is just equal to 0. So that's a nice mathematical way we can find the value of the negation. Let's take a look at connectives that involve more than one statement. So for example, conjunction. And you will see either the caret, the and symbol, or the dot for conjunction. I will always use the caret because it's typically used in most discrete math texts. Okay, so here, conjunction, it takes two statements and combines them. So how do we build a truth table for two statements? Well, Q can either be true or false. And P can be true or false. So all possible combinations, well, Q can be true, false, and then P, well, there's two situations where P will be true and two situations where P will be false. And now we can see that we have all possible combinations of P's and Q's. So if we have two statements, we need 4 rows, because each one can be true or false, which means that there's 2 possibilities for Q and 2 possibilities for P, which means we need 4 rows. If we had another statement R, then we'd need another doubling, because R can be true or false, and we need 8 total rows. So the number of rows is equal to 2 raised to the number of statements. So that's just building a truth table. Now, what does P and Q do to the truth value? Well, P and Q is true only if P is true and Q is true. So it's only true in the first scenario where both P and Q are true. In every other scenario, it is false. So what's a mathematical way of looking at this? Well, we say that the value of P and Q is just equal to the minimum of P and Q. So for instance, the minimum of P and Q in the first row is 1, because the lowest value between P and Q is 1. In the second row, the minimum of P and Q is 0, because Q is the lowest value. In the third row, P is the lowest value at 0, and in the fourth row, both P and Q are 0. So that's conjunction. And of course, conjunction is and. let's take a look now at disjunction. And disjunction, you'll either see the V or you'll see a plus sign. The plus sign more in abstract Boolean algebras. But what does P or Q do? Well, P or Q is true if at least one of P, Q are true, which means in the first row it's true because both are true. In the second row it's true because P is true. In the third row it's true because Q is true. But in the fourth row, neither P nor Q are true, therefore P or Q is false. So again, mathematically we can think of this as P or Q just takes the maximum of P and Q. So in the first row, both are 1s. 1 is the highest value, so it's true. In the second row, P is a 1, that's the highest value, therefore it outputs a 1. In the third row, Q is a 1, which is the highest value, which means it outputs a 1. But in the fourth row, the highest value is 0, so we output a 0. That is disjunction. Now what about the conditional? In the conditional, we usually see the arrow, and occasionally we see the superset symbol, but this is more for philosophical logic and not seen too much in any math texts. So this is an interesting one. This is the truth condition for if P then Q. And it is only false if P is true and Q is false. The rest of the times it will be true. And this is kind of hard to wrap our brains around. And I'll emphasize this more in an upcoming video on just conditionals on their own. But for now, let's say that I tell you, if it's sunny, I will wear sunscreen. So let's say I tell you this. When am I lying to you? I am lying to you if it is sunny out, which would be P is true, and I'm not wearing sunscreen. This is like my promise to you. I'm saying, look, if it's sunny out, I promise I will wear sunscreen. And if it is sunny and I'm not wearing sunscreen, I lied to you. Therefore, the conditional is false. But if it's not sunny outside, well, I'm not lying to you, am I? It doesn't matter if I'm wearing sunscreen or not. It's not sunny outside. Therefore, I'm not violating any truth conditions. Therefore, it is true in the bottom two cases. And this is a very difficult thing to wrap our heads around because we think, well, if it didn't happen, then we can't say it's true or false. But think of the conditional in terms of, when am I lying to you? I'm only lying to you in this one situation. So we say that, mathematically anyway, P arrow Q is 1 if the value of P is less than or equal to Q. So in the second scenario here, 1 is not less than or equal to 0, therefore we get a 0. But everywhere else, P is less than or equal to Q, so we output a 1. And that's a mathematical way of looking at things. If the explanation reasoning is just a little bit too confusing, or maybe you don't accept it, we can just define it in terms of these mathematics here. So those are the 4 main connectives and their truth tables. But there's 2 more connectives that we can define in terms of the other connectives, but let's just treat them as if they're their own connective for now. The first one is the biconditional, and this is usually if and only if. So this is written if with 2 F's, or just if and only if. And typically, we'll use the double arrow here. However, some texts use the equivalency symbol. This is like kind of weird to use. I would never use this myself, but I've seen it before, so I'll write it here just in case you encounter it as well. And the way P and Q works, or P if and only if Q works, is if P is equal to Q, then we have that P arrow Q is equal to 1. So if they're the same value, it outputs a 1. So when P and Q are both true, the biconditional is true, and when P and Q are both false, the biconditional is true. If the values are separate or different from each other, then it's false. So in the second row, P is 1 and Q is 0, therefore it outputs a 0. if P is 0 and Q is 1, it outputs a 0 because the values aren't the same. That's the biconditional. Finally, we have exclusive OR. And exclusive OR is really our idea of what OR means in English. So this is the opposite of the biconditional. So if P is not equal to Q, then P exclusive OR Q is equal to 1. And typically we see it with the circle with the line through. We might also see the disjunction with the little underline. Both are commonly used. I like the circle because it's very obvious that I'm talking about exclusive OR, and we also use the same symbol in set theory sometimes. So it's just the opposite of the biconditional. So P true and Q true means that P exclusive OR Q is false. And similarly, if they're both false, then that also outputs a false. But if the values are different, such as in rows 2 and 3, we get true. So those are truth tables. And in the next video, we'll learn how to use these connectives and truth tables to prove that two statements are logically equivalent.